So, good morning everyone. I hope you can hear me well. So, today's topic of lecture: solutions of electrolytes, pH and buffer solutions. So, let us start. So, everybody knows that aqueous solution of some substances like salts, acids, bases conduct electric current. But some solutions like aqueous solution of glucose, sucrose do not. So, electrolytes are compounds which dissociate into ions when dissolved in water, and that's why they conduct electricity. As examples of electrolytes can be mentioned inorganic compounds, salts, acid, bases, but also we have polyelectrolytes as a biochemically important substances. They behave same way because of consist some number of functional groups can become charged in aqueous medium. Behavior of electrolytes solutions described with the help of Arrhenius theory of dissociation of ionization or ionization. The difference I will explain a little bit later. The first one, when electrolyte is dissolved in water, it splits into ions, positively and negatively charged. So positively charged ions are named cations and negatively charged ions are known as anions. So what there happened when electrolyte dissociate into ions? Some number of molecules can dissociate. In some cases, some number of molecules are not. The ratio shows how well electrolyte dissociate into ions can be expressed with the help of Van Hoff's factor, also known as degree of dissociation, I. It shows the total number of particles in a solution, number of molecules which not dissociate, and number of ions are produced to dissociation, to the total number of particles supposed to be according to the concentration. Dissociation is a reversible process. So except dissociation or ionization, sometimes used as synonym, the opposite force, molarization, can be mentioned here. As you can see, forward and backward arrow both. It doesn't mean that molarization with the formation of real molecules happen. No. When electrolyte dissociate into ions, positively and negatively charged, definitely these ions attract to each other and formed some kind of ionic pairs. So interionic interaction, the reason why when we measure conductivity of any electrolyte solution, usually we see lower value of conductivity than supposed to be according to dissociation. So it's a reversible process, see? So that's why the equilibrium appears. When equilibrium appears, we know how to describe how to effect dissociation. That Leach-Atelier's principle here can be also used if we want dissociation happen better or worse. And I want to remind you something we did the last lecture. We explained there why aqueous solution of electrolytes have sometimes quite high difference colligative properties of solutions. Remember, colligative properties of solutions are properties depends on nature of electrolyte, or not electrolyte but solvent, and number of solute particles, not the nature of solute, number of solute particles. So if we deal with non-electrolyte, their number of solute particles and concentration we can say same. But electrolytes, as they dissociate completely or not, their number of particles in solution much higher, 2, 3, 5 times higher than concentration initial given. So that's why isotonic coefficient, Van Hoff's factor, here should be used to describe the behavior of electrolyte affecting the boiling point elevation, freezing point depression, and osmotic pressure. Osmotic pressure of electrolytes extraordinarily higher than osmotic pressure of non-electrolyte. So, very important characteristic of any electrolyte is degree of dissociation, alpha. It's a fraction of total number of molecules of an electrolyte which splits into ions. it can be expressed in percent, can be not. So total number of particles, molecules of electrolyte which splits into ions. So here it's very important to understand one thing, that when we deal with different nature electrolytes, they can be classified into three types according to the value of this degree of dissociation or ionization. There can be three. Strong, really dissociate completely. So strong electrolytes, alpha supposed to be 100%. They are usually ionic solids, not only some molecular compounds also, but you know, for example, salts, all soluble salts dissociate completely. Not step by step, not partially, dissociate completely if it's soluble salt. So alpha is supposed to be 100%, but because of interionic interactions, the real value of alpha we measure, it becomes lower, and more than 30% already acceptable as a strong electrolyte. As more diluted solution, as closer alpha to be perfect, to be 100%, but usually never perfect. Ideal solution, you know, where interionic interactions not present, not exist. So weak electrolytes with the alpha less than 3%. As example, we can take any weak acid like acetic, like carbonic and others, and some weak bases. From soluble bases, you should know only ammonia solution or ammonium hydroxide, you know, sometimes it's named like this. And between these two values, it's medial strong electrolytes. So alpha from 3 to 30%. As example, here can be mentioned phosphoric acid. First step, it dissociate as a medial strong. So let us try to understand what's happened when substances dissolve. There are two types of compounds behave as electrolytes when they dissolved in water. First one, it's ionic solid. So ionic solid already in crystalline lattice consist ions. Ions not formed when these substances dissolved in aqueous. Water, dipole ionic interactions, water helps these ions to be released. So water is a reason of these ions released, but not formation of ions. They are not no formation. Ions are just sets free. For example, any soluble salt, sodium chloride, dissociate in aqueous medium, forming sodium positive and chloride negative. The next type of electrolyte, it's a molecular compounds, consist polar bond. Now, for example, HCl. So what is there? There are no ions yet. They are covalent polar bond between hydrogen and oxygen. Because of water, dipole-dipole interactions, polarization of the bond happen, and the most electronegative oxygen acquires one negative unit, -1, and the hydrogen part become +1. It's obtained +1. So ionization appears, ions are formed and then dissociate. So see, dissociation happens through formation of ions. As ionization gradual, that means it happens step by step. That's why dissociation of compounds molecular nature also can happen with step by step. For ionic solid, it's not possible. They are always dissociate same moment without any steps. So here acid is monobasic, that's why dissociate within one step. But if we will take any example of di or triabasic, I will show you then, there will be step-by-step dissociation. So let us start with the weak electrolytes. First of all, behavior of electrolyte, weak electrolyte in a water depends on nature of this electrolyte. As a covalent bond to be ionized, there can be different polarity, more or less polar bond. That's why it can ionize easier or worse. So it's a nature. It can't be described with any mathematical formula, just experimentally can be measured. So let us compare dissociation or degree of acetic acid. Dissociational constant of acetic acid, it's 1.76 times 10 power negative 5, and alpha 1.32%. For HCN acid, hydrocyanic, dissociational constant approximately 6.2 times 10 power negative 10. There 10 power negative 5, here 10 power negative 10. And as you see, alpha really much smaller value, 7 times 10 power negative 3%, very small. Second factor affecting the dissociation degree, so that means how well this weak electrolyte dissociate into ions, it's a concentration of solution. Ostwald dilution law, the mathematical formula I will show you then. As low the concentration, as high the dissociation degree. This is true for weak electrolytes. And the last but not least factor, it's a temperature. As high the temperature, as high the dissociation degree. Here it's possible to understand because of usually solubility. Also, they are due to solution dissolved in aqueous medium. They are not just ions are formed. They are formed hydrated ions or solvated ions if we deal with any solvent except water, solvated or hydrated. That means every ion attached to the water molecules. So, as their equilibrium appears, remember, as higher the temperature, equilibrium with the temperature shifts to the endothermic. Usually formation of hydrates, it's an endothermic process. That's why temperature, but in exact limits. Boiling point, water already can't help to dissociate. It's worry about formation of vapor. So that means within some interval, temperature really helps dissociation happen better. Polarization happen faster, and that's why dissociate better. But again, this is important for weak electrolytes. As strong electrolytes, we know dissociate completely. Doesn't matter what temperature. One more very important characteristic, we can say the strength of any electrolyte can be described with the help of dissociational constant. In all tables it mentioned as ionization constant, as it more general. An equilibrium constant of an equilibrium between ions of weak electrolyte and unionized weak electrolyte. As weak electrolyte never dissociate completely, there are some concentration of undissociated, unionized electrolyte molecules present. So what we can use as example here? The standard example always, it's acetic acid dissociation. It's a monobasic, that's why not gradual, within one step ionization, and that's why dissociation also happen within one step. So it's ionized and dissociate, forming one proton, positively charged ion, hydrogen ion, and acetate ion. So equilibrium appears, that's why equilibrium constant, as you remember, it's a mathematical product of concentration of products in power of balance coefficients over mathematical product of concentration of reactants in power of balance coefficients. But here only one reactant, so that's why concentration of this in equilibrium, acetic acid. This equilibrium constant, because of its dissociation of acid, known as Ka, dissociational constant of acid. For base it will be Kb. These values are tabulated. You shouldn't memorize them, but you should know that for strong electrolyte dissociational constant, its hypothetical value can't be used for concentration, as their interionic interactions very strong, and equilibria, it's hypothetical situation. Formation of ionic pairs. Only for weak electrolytes, these values we can use to determine something mathematical. So if they are di- or triabasic acid molecular compound, as I told you, dissociation happens gradually, step by step. Because of ionization also happens step by step, formation of one positive, one negative, and then if it's possible, ionization happen next step. So for example, carbonic acid, which is diabasic, dissociate first step, forming proton and hydrogen carbonate ion, and here dissociational constant of carbonic acid first step, it's a mathematical product of proton concentration and hydrogen carbonate ion over undissociated value of carbonic acid. The value is 4.5 times 10 power negative 7, quite small. It's a weak electrolyte. But this reaction, this ionization process happened then. Second step, hydrogen carbonate ion also ionized and dissociate into proton, 1 positive, and carbonate ion with the charge -2 achieved. So dissociation of constant second step, it's a mathematical product of concentration of proton and carbonate ion over undissociated hydrogen carbonate ion concentration. The value of dissociational constant 4.8 times 10 power negative 11. Take a look. 10 power negative 7 first step and 10 power negative 11 second. 10 power 4 times difference. That's why definitely we can't say that it dissociate 2 steps in moment. Even if mathematically we can find the average of these 2 dissociational constant. The physical meaning, the amount, not allow us to say that it's this dissociation happened really according to the formula 2H plus carbonate ion 2 minus. You should know one more thing, that dissociational constant first step always higher than dissociational constant second, and then third one, if like for phosphoric acid, it's happened next step. So if we will try to measure using just lab equipment conductivity of water, it seems like water non-electrolyte. But if we will use some sensitive equipment, there you will see that water conduct electricity, very, very small extent. Water is very, very weak electrolyte, but it dissociates same concentration proton and hydroxide ion, very small value, and this process is known as self-ionization of water because of it ionizes itself. Self-ionization of water. So dissociational constant for this self-ionization is the same as before, mathematical product of concentration of product, that's mean proton and hydroxide ion concentrations over undissociated water concentration. And it's equal to 1.8 times 10 power negative 16. As you see, extraordinary low, but it can be measured. So what do we know about concentration of undissociated water? So undissociated, so the water amount which is really dissociated according to this value 10 power negative 16 is negligible. It's very, very small if to compare with undissociated one. So that's why here this equilibrium constant of water approximately equal to initial concentration of water, which is standard value. If we take standard condition 25 Celsius as a mass of water, density of water is 1 gram per milliliter, and in 1 liter we can say 1000 gram. So the concentration of water is a standard value, constant value 55.56 mole per liter. So denominator is constant, dissociational constant as well. That's why their mathematical product is constant, and if you will multiply 1.8 times 10 power negative 16 times 55.56, you will get 10 power negative 14. This constant is known as ionic product of water and Kw. It's always same for any aqueous solution. So that's why what we know, ionic product of water, Kw, it's not dissociational constant of water. Be attentive. It's always constant, 10 power negative 14, and it can be expressed as mathematical product of concentration of proton and concentration of hydroxide ion. Always same for any aqueous standard condition. So concentration of water, concentration of proton, concentration of hydroxide ion. Usually when we deal with aqueous solution, they are quite small, they are powers, and it's very hard to deal with. So century ago, approximately, no, 100 years ago, I'm sorry, there was proposed to use more useful, easier scale known as pH scale. What is pH? Sorensen proposed this. So pH scale, pH, P it's small, it's a minus decimal logarithm. So pH scale means that, let us see, that if we will take minus log of concentration of proton for pure water, it will be equal to 7. So it's a standard value for neutral solution where H plus and OH minus equal to each other and equal to 10 power negative 7, as their mathematical product is 10 power negative 14. pH equal to 7 means neutral. It's a pure water. And if we will add in this, so pH scale from 0 to 14. 0, it's something like hypothetical aqueous solution where no hydroxide ion at all. It seems like dissociation depressed and only protons are present there. And 14 pH, it's a situation where hydroxide ion the maximum and seems like proton concentration depressed. So inside this interval we're dealing with different types of solution. So if we will add some protons, using some acidic solutions, acids or acidic we will deal with, then you will see the hydrolysis appears and acidic medium also can be produced. So acidic solution, they have higher concentration of proton than neutral. That's mean H plus more than 10 power negative 7 mole per liter. If we take minus log, we will see pH for this solution less than 7. Everybody knows. And basic solutions with the hydroxide ion higher value than proton concentration, and that's why pH more than 7. So if we deal with acidic solution, it's clear. Proton concentration we can determine, we know, and that's why pH easy to deal with. But we can deal with the basic solution where hydroxide ions are known, concentration of them, and that's why in such case easier to deal with a pOH scale. pOH, it's a negative log of hydroxide ion concentration. So that's why base given, we can find pOH, and because of ionic product of water we know that mathematical product of concentration of proton and hydroxide ion is constant value. If we will take minus log of left and right side, we will get same ionic product of water, but in pH scale, pH plus pOH always equal to 14. That's why due to what pH or pOH we should find, we can find one of them and then as a 14 minus second determine what is the question task. So there are some biological liquids. We will not insist you memorize all of them, as you will deal with the pH values of biochemically important liquids, biological liquids in our body, in normal physiology. It's a third year subject. Now this year you should memorize just some to use them to predict something very important from chemical point of view. So what you should know better as your own name, it's a blood plasma pH. Blood plasma pH, as you see, blood plasma and spinal cord liquid, they are same value of pH. It's a quite strict value, 7.4 plus minus 0.05. What's mean? The normal value of pH for blood plasma, it's an interval from 7.35 to 7.45. Within this interval, everything fine. It's a normal pH of the blood plasma. Saliva, as you see, it's slightly but acidic. Gastric juice, quite strong acidic, as you see, because of HCl presence. Urine, it's an interval from acidic through neutral to a little basic. So that's why pH information important when we analyze urine test, but not enough to know to put some diagnosis. Now in spinal cord, as I told you, it's the same value as blood plasma pH. So what is here important to understand? That there are blood pH imbalance can lead to two conditions. It's acidosis and alkalosis. What is acidosis? It's a shifting of pH of blood in acidic medium. That means lowering from normal value of 7.4. That means lower than 7.35. This is already will be acidosis. Classification I will mention then. The maximum value of shifting pH in acidic part, it's a 0.6. That means the lowest value 6.8. Then death already. Alkalosis, it's a shifting of pH of blood in basic medium with increasing from normal value 7.4. Here shifting of pH not happens such higher as for acidosis, just 0.4. Then already coma and death. So in acidic medium 0.6 maximum, and in for alkalosis 0.4 maximum. So what we know about acidosis, alkalosis? So there are a lot of classification, really 3 or even 4. You will learn more exactly in normal physiology and pathological physiology. So now I just want to mention some of them. You understand what is. So first of all, the shifting can be compensated, sub and uncompensated. Compensated acidosis, alkalosis mean that pH value is normal, but there are already some processes appears. So it's within the interval 7.35 to 7.45, but some symptoms already present. Decompensated or uncompensated, if they are lowering lower than 7.35, that means till 7.29 it's a subcompensated, and lower till 6.8 it's already uncompensated, coma and death. It's a serious problems with health. So alkalosis same, but shifting, as I told you, lower value, just 0.4. So that's why till 8 not. So there are types according to the reason. Can be respiratory or respiratory acidosis and metabolic. Respiratory or respiratory acidosis is caused by your lungs because of they are not able to remove enough carbon dioxide when you exhale. This can occur when your lungs are affected by some diseases or other disorder. Now, what, for example, everyone knows some disease like asthma. It can be reason of such kind of acidosis, emphysema of lungs, no, and pneumonia. Now quite modern. So, it can be also caused by some narcotics and sleep medication. So what primary symptoms of respiratory acidosis? It's sleepiness, extreme, fatigue, confusion, and headache. And if you suffer because of headache, it doesn't mean that you have acidosis. Acidosis and alkalosis, it's not exact diagnosis. It's kind of symptoms, right? Disorder. Diagnosis, it's a little bit different. So, and again, shifting in a too strong acidic medium serve coma and death. So what about metabolic acidosis? Metabolic acidosis, the reason because of some extra acids produced by kidneys. It occurs when your body can't get rid of excess acid or loses too much base. Specific causes include their, for example, having too little sodium bicarbonate in your blood because of vomiting or diarrhea. Ketones due to lack of insulin. That's why what kind of diabetes mellitus. It's a reason of acidosis, metabolic nature. Alcohol measures, cancer, seizures, and so on. So also can be some medications like aspirin in large doses can leads to this type of acidosis. Methanol, antifreeze, such substances, toxic, also leads to this. What alkalosis? Alkalosis not happen so often, and why I will explain later. But it also can be classified as respiratory and metabolic. Respiratory alkalosis, and when there is too little carbon dioxide in your blood. So causes of respiratory alkalosis includes hyperventilation due to anxiety, aspirin overdoses, higher fever, and possibility even pain. If you remember, we discussed last time such problem as mountain disease. There was a summation of symptoms because of lower pressure, and that's why lower solubility of oxygen in blood, but except oxygen in the air present carbon dioxide we breathe, and it stimulates breathing center, and when it dissolves in blood it's keep acidity normal. So higher mountains, more than 2000, 4000, so on, solubility of carbon dioxide because of low pressure as well becomes lower, and that's why alkalosis can be affected by this. So metabolic alkalosis occurs because of bicarbonates levels in blood too higher. Bicarbonates cause basic medium, or your body loses too much acid. So long period of vomiting, over diuretics, for example, and so on, can be the reason of alkalosis. The most often it's a hospital alkalosis because of wrong pH intravenous feeding. That means it's a doctor's mistake. Unfortunately, happen because of we need to use pH normal value for intravenous feeding as well as osmotic pressure supposed to be normal. So 7.4 slightly alkaline. If they mistake and two alkaline solutions, a solution alkalosis appears as a result of this hospital alkalosis. So there are three types of theories describe behavior of acids and bases. So acids, Arrhenius theory is the simplest one when we deal with inorganic compounds. Arrhenius theory states that electrolytes acids are strong or weak electrolytes, dissociate, producing only one type of positively charged ion, protons. So they are proton donor, but as electrolytes. Bases are electrolytes, dissociate in aqueous medium, producing only one type of negatively charged ions, are known as hydroxide ions. That means, according to Arrhenius theory, acids and bases are electrolytes. But not all compounds are able to dissociate in aqueous medium, but they behave as acids or bases. So that's why second acid-base theory, it's a Lowry-Bronsted or Bronsted-Lowry theory, and it changed definition to just proton donor, proton acceptor, more acceptable for organic compounds because of mostly they are non-electrolytes. And Lewis theory, as you remember, Lewis acids, we use quite often as a catalyst. It's a now change definition, nature of acids and bases, not to the donor and acceptor of proton, but combine it with a electron pair, donor or acceptor. So acids are non-electron pair acceptors or non-bonding electron pair acceptors, and bases non-bonding electron pair donors. So it's clear when we deal with the acid, we add to the aqueous medium, and that's why as proton donor, our acids dissociate, forming base acidic medium. When we add alkali, hydroxide ion formed due to dissociation, and that's why basic medium. So shifting of pH from normal happen because of we add exact nature ions, protons or hydroxide ion. But there can be situation where dissolved compound not consist at all any proton or hydroxide ion in a structure, even being ionic solid, but the medium somehow become acidic or basic. This happens because of some salts undergo hydrolysis. I hope you remember what is. It's a chemical reaction of salts with water due to produce acidic, basic or neutral medium. Hydrolysis happen not only salts undergo hydrolysis. There are a lot of biochemically important substances in our body undergo hydrolysis, like proteins, nucleic acids, lipids, and so on. So hydrolysis is quite essential. It's a chemical reaction with water. So, but hydrolysis of salts change the pH medium. Not all salts undergo hydrolysis. There are really 4 types of salts, but only 3 types of hydrolysis. So first one type of salt, ionic solids, soluble salts or non-soluble. Mostly we deal with the soluble, definitely. Salts of strong base and strong acid, like sodium chloride, like potassium sulfate, and so on. The strong list of strong bases we know as alkalis. You must know they are just few. It's a sodium potassium hydroxide and barium hydroxide from the second A group. Lithium hydroxide, it's closer to be medial strong. Other can't be strong because of the insoluble. So strong acids, there are not so many as well. It's hydrochloric, hydrobromic, sulfuric, nitric, perchloric, and chloric. There are not so many. When these acids and bases combine forming salt, there are such situation happens. Such salt seems like should react with the water. It's an ion exchange backward to neutralization, producing HCl acid and sodium hydroxide. If we will write ionic equation, we will see that sodium chloride as a soluble salt, it's a strong electrolyte, dissociate completely and present as separate ions. Water weak electrolyte, that's why in ionic equation we can't show it as separate ions. Hydrochloric acid, strong acid, present as separate ions. Sodium hydroxide, strong base alkali, present as separate ions. If we will cancel left side and right side same ions, not take part in a chemical reaction because of nothing new is formed. So we will see that only self-ionization of water happen. pH is neutral. Hydrolysis does not happen. There are no hydrolysis reaction, just formation of hydrates. That's it. So no change in pH. If there we will combine strong with weak or weak with weak, the hydrolysis happen with change of pH. So if there is salt of strong base and weak acid, like sodium acetate, sodium hydrogen carbonate, essential one we will discuss then, potassium sulfide, any strong with weak, what we see? If it's soluble, that means dissociate completely into ions. So, and as a result of chemical reaction of this salt with water, we have weak electrolyte, in our case acetic acid, which not dissociate completely, that's why in ionic equation present as a molecular. And sodium hydroxide, in this case it's a strong alkali, it's a dissociate completely into ions. So just sodium we cancel, and then we see that only weak anion, in this case it's acetate ion, chemically react with water, forming the new substance acetic acid. Strong electrolyte sodium hydroxide, sodium not react with the water, their hydrates only formed, but it's affect the medium. Strong part affecting the medium, weak one react with the water. So that's why C, salt of strong base, weak acid, the basic medium, pH more than 7. Same situation happen if there's salt of strong acid and weak base, like ammonium chloride, ammonium sulfate, aluminium bromide, zinc chloride, doesn't matter. Weak base, strong acid. Strong acid, that means supposed to be acidic medium. Let us see is it truth or not. Ammonium chloride with water, supposed to be ammonia times water or ammonium hydroxide hypothetical, plus HCl, which is strong. Only strong electrolyte dissociate completely. That's why ammonium chloride is a soluble salt present as separate ions in aqueous medium, and HCl is a strong acid also present as separate ions. Ammonium hydroxide is a weak base. So we cancel only chloride ions, and what we see? Only weak component of this salt react with the water, ammonium ion, forming ammonium hydroxide, and proton changes the medium into acidic. See, it's truth. Weak base, strong acid, acidic medium. If you need to predict the medium character, you will do this using just information about which one strong, which one weak. If you need to determine the medium, there are already different steps. So, what to do if they are both are weak? If they are both are weak, we need still to compare which one weaker, which one stronger. The one stronger producing the medium. But there are no ionic equation possible to write, and they are even salt being completely dissociated. We can't cancel anything, and then new products are formed. For example, ammonium acetate with water, forming ammonium hydroxide and acetic acid. Both are weak. Both dissociate quite slightly. And if we will check dissociational constant, which you shouldn't memorize, they are tabulated. Ammonium hydroxide, for ammonia, dissociational constant equal to 1.74 times 10 power negative 5. 1.74 times 10 power negative 5. For acetic acid, the value 1.76 times 10 power negative 5. They are approximately equal to each other. That's why solution of ammonium acetate is neutral. Their hydrolysis happen. We can find ammonium hydroxide and acetic acid. We can find them in this solution, but pH 7 as their dissociational constants are approximately equal to each other. If both are weak, but one bigger, so dissociation constant of base bigger than acid, it's basic medium. Acid dissociational constant bigger than dissociational constant of base, it's acidic medium. So necessary just to use information which is tabulated. But there are some solutions exist when we add acid or base little amount, somehow pH doesn't change significantly. We add strong acid, but solution still same value of pH. Such solutions are known as buffer solution, and solution whose pH value doesn't change significantly upon the addition of small amount of strong acid or base and dilution. That means addition of water from outside. Buffer solution, it's never individual substance solution. It's a mixture for at least two components mixture. Now we will discuss the easiest case of buffer solutions, a mixture of two components. Next year in biochemistry you will see that buffer solution can consist more 3 and even 4 components. So there are two types of two-component buffer solution. Can be acidic buffer solution and basic buffer solution. Acidic buffer solution, it's a mixture of weak acid and its salt with a strong base. So we use salt with a strong base. A strong base is sodium, potassium. Salts are soluble all, so that's why dissociate completely, and that's why we can say that acidic buffer formula, it's an anion of acid and weak acid. As example of acetic buffer, we can mention acetic buffer. No, it's acidic buffer. Acetic acid with a sodium or potassium acetate. Carbonate buffer, biochemically important one, it's a mixture of carbonic acid, more correct to say CO2 times H2O, and sodium hydrogen carbonate, it's a carbonate buffer. Take a look, weak acid and weak acid anion, HCO3 minus, hydrogen carbonate ion. Basic buffer, it's a mixture of weak base and it's salt with a strong acid. Again, as we take strong acid, dissociate into ions completely. So that's why we can show the formula of basic buffer as a protonized base and the base itself. So ammonium buffer, it's only one basic buffer. In inorganic chemistry, we deal with NH4OH, so ammonium hydroxide, or can be just NH3 plus NH4Cl or any ammonium salt like nitrate, for example. We're trying to avoid sulfate because of sulfate then can form precipitate with different types of substances we add. For example, alkali barium hydroxide we can use to shift pH. And the problem is barium sulfate, it's an almost insoluble compound forming precipitate. We want to avoid this. That's why nitrate, chloride or bromide more often. These anions usually soluble. Not always, but soluble. So, what is the idea of buffering? Let us take again as example acetic buffer, which is mixed of acetic acid and it's salt with a strong alkali, sodium or potassium. When we add, so why there are two components? One of the components should neutralize acid added and second one base added. So let us see what's really happened. If we add a little amount of strong base, few drops, because of buffering, it has some limits. So we're talking about little amount. If we will add a lot, definitely pH will be changed significantly. Little amount, few drops of strong base, like sodium hydroxide. Usually we prefer to add same base, same alkali, as a salt cation. So sodium hydroxide to acetic acid, what's happened? It's a neutralization reaction. Formation of salt and water. Neutralization, the idea of neutralization, to neutralize the medium, to get neutral pH. So what is here happen? Acetic acid is a weak electrolyte. That's why in ionic we will not show a separate ion. Sodium hydroxide as a strong alkali, dissociate completely. Soluble salt, sodium acetate, dissociate completely, and water is a weak electrolyte, will not dissociate completely, can't be written as separate ion, will be written as molecular. Sodium cancel, and as a result we see what's happened. When we add strong base, OH minus, weak acid, neutralize this hydroxide ion, forming acetate, not produce any proton or hydroxide, and water. The problem when we say pH doesn't change significantly, it seems like here shouldn't be changed at all, but neutralization reaction is reversible. Hydrolysis happen backward, a little extent, but happen. That's why we're saying pH doesn't change significantly, not absolutely. What will happen if we will add some amount of strong acid, hydrochloric or sulfuric or nitric? Really, again, just few drops. So what has happened? Acid react with a salt. Salt is a second component which is neutralize acid effect. Formation of weak acid and salt, in our case it's a sodium chloride. Ion exchange reaction. If we will write ionic equation, we will see that there again sodium and chloride ions are cancelled. And as a result we see net ionic, where acetate ion with a proton forming acid. So take a look. We add strong acid, H+, should affect pH quite effectively. But it's react with the acid, salt anion, forming weak acid, which dissociate less. It dissociate less, should affect pH value less, but it still should affect. So what's really happened there? When concentration of weak electrolyte acid rising according to Ostwald's dilution law, alpha dissociation degree, which is equal to approximately square root of the ratio dissociational constant of acid per concentration of this acid. Take a look. What's happened? Concentration of weak electrolyte rising, that's why dissociation degree becomes less. And that's why pH doesn't change significantly. Again, not absolutely, significantly. Acid neutralized by weak acid and base alkali neutralized by the salt. But it's not happen, as I told you, till any acid we add or base. There are limits. So how to understand how well buffer solution works? First of all, we need to understand what pH it's resist changing. So buffer solution not resist changing pH from 7 to some. Every buffer solution has its own value of pH. So how to determine the buffer solution pH? It's a Henderson-Hasselbalch equation. For acidic buffer, pH of buffer solution first of all depends on dissociational constant of acid, which is component of this acidic buffer. It's a first factor affecting pH. pKa means minus log of dissociational constant. All these values are tabulated. Second factor, not so effective, but also affect the value of pH of buffer solution. It's a logarithm of the ratio salt concentration over acid concentration. See, pH of buffer solution never depends on concentration of acid or base, but the ratio. So, the first, again, the major factor affecting pH of the buffer solution is dissociational constant. Then a small amount, because of log of this ratio, it's quite small amount, we can vary the value of pH, plus, minus, but little amount. Effective, but not as much as pKa. For basic buffer, pOH can be found with the same formula as a hydroxide ion, some amount present. So pOH is pKb plus log salt over base. But we know the ionic product of water help us to determine pH if we deal with pOH. So that's why pH, according to Henderson-Hasselbalch formula, can be equal to 14 minus pKb, and here plus log of the base over salt or minus log of the salt over base, due to which one higher and easier to determine. So why minus? Because of when we open the bracket, sign plus should be changed into minus. So again, for basic buffer, we can find pOH first and then just pH as 14 minus pOH. Or we already can put this 14 minus in a Henderson-Hasselbalch formula to calculate once. So changing base and salt position, we can change minus and plus here. If base over salt, there will be plus log. Salt over base, minus. So some buffer solution resist change in basic medium, for example, like carbonate buffer. Some in acidic medium, like acetate buffer, due to what is dissociational constant value. So what is a buffer capacity, capital B as a symbol? Buffer capacity physical meaning, it shows the value, no better to say even how long buffer solution resists change in pH. How long, how effective it is. Mathematically, it's equal to amount of strong acid or strong base that can be added to certain volume of buffer solution before the pH begins to change significantly. So see, amount of acid or base will not change pH significantly. Next drop of acid or base, pH already changed significantly. So that means it shows how long it resists change in pH. As high the buffer capacity, as longer the solution works buffering way. So how to determine buffer capacity? So for different types of stressful factors, it can be acid added, strong acid or strong base added. So it can be buffer capacity by acid and buffer capacity by base. So buffer capacity by acid, it's a number of moles of strong acid. So that's number of moles, as you remember, it's a product of concentration of acid and a volume of acid over delta pH, the change of pH caused by this addition. And in denominator you see volume of buffer solution. So it's a buffer capacity by acid. If we add buffer capacity, if we add base to the alkali definitely to the buffer solution, buffer capacity by base, it's a mathematical product of concentration of base, strong base, and volume of strong base. That's mean number of moles of this strong electrolyte over delta pH caused by this addition and volume of buffer solution. So usually it's not same. Buffer capacity by acid and buffer capacity by base for our buffer solution neutralize both same way. It's never happen. Usually one of the buffer capacity is higher. No, so it will be equal, no, let us say the maximum. The highest buffer capacity by acid and by base will be if concentration of weak acid and salt or weak base and salt in buffer medium are equal to each other. That's mean according to Henderson-Hasselbalch formula. Let us come back to this. Take a look. If salt and acid or salt and base concentrations are equal to each other, their ratio 1, log of 1 is 0, and that's why pH become equal to pKa. That means it seems like this buffer solution neutralize acid, strong acid, which is salt neutralized, and strong base alkali, which acid should neutralize. Same way, buffer capacities are equal. Usually it's not same. So what is the biochemical importance of all we discuss about buffer solutions? As we know already that shifting of pH of blood cause serious problems and even death. Our blood should somehow, and other biological liquids as well, should resist change in pH because of people suffer because of some different diseases. We eat something, we take some drugs, for example aspirin, which is acidic medium, but pH doesn't change significantly. They resist. It's the blood, urine and other liquid, they resist change in pH. Why it's so? Because of their buffer solution present and not only one. In blood plasma there are 3 buffer solutions present. The major one is a carbonate buffer or bicarbonate buffer. It's a mixture of weak acid, carbonic acid, more correct to say CO2 times H2O, and their hydrogen carbonate ion. Bicarbonate buffer, it's a main, the fastest, the most effective buffer solution, resists change in pH when its acid appears in the blood. Breathing some extra amount of carbon dioxide, some medicines. Within seconds it acts buffering, neutralizing this extra acid added. Then already kidneys. Kidneys works longer, but it's already hours. The first factor helps our blood to resist change in pH. It's a carbonate buffer. To understand that acidosis and alkalosis happen different extent, so our body resist, as I told you, delta pH in acidic medium higher than delta pH in basic medium. For acidic medium 0.6, for alkaline medium 0.4, and it's proved by the amount of carbonate ion and acetic. Carbonate ion higher almost for 20 times concentration than acetic acid. So that means our buffer solutions, our blood, more readily, longer, buffer capacity higher by acid than by base. Phosphate buffer, second importance for blood plasma, but one of the major important for urine. So phosphate buffer, it's not just a phosphoric acid. Phosphoric acid itself not present there. It's a mix of 2 salts, dihydrogen phosphate and a hydrogen phosphate ion. The one with a higher amount of H+, it's an acid, acts as a weak acid, and this one acts as a salt. Hydrogen phosphate 2- as a salt. Also higher concentration of salt, but now 4 times approximately higher acid, salt to acid. And the third one importance, that's a proteins buffer. What's important to understand here? That whole blood. So in blood plasma there are no red blood cells. But when we deal with whole blood, the major buffer solution, it's a hemoglobin buffer, the one inside the blood cells. Hemoglobin, oxyhemoglobin buffer, it's approximately same thing. I mean, when we explain buffering, bicarbonate buffer inside red blood cell, it's a third, even fourth important one. Hemoglobin, oxyhemoglobin, proteins buffer, they are much more effective inside. Bicarbonate buffer, very effective outside in blood plasma. So in our body we have a basic buffer. It seems strange, but we have ammonium buffer, but it's present in urine. In blood, never. So I think this is it. Very fast, within 1 hour. But it's I don't want to give you some examples how to calculate this information given in your home task as a teaching tasks. If something not clear, then you can ask for consultation. It's not a problem. Now, if something not clear in this lecture, please write in a chat. I will try to explain and understand. You will understand what is. So think and tell me, is there any questions about the topic we discussed just now? Think, maybe you missed some slide explanation. I saw some students miss the beginning, so unacceptable. You know the lecture time, and some messages I got today's morning about, please ma'am, convert Moscow time in Nigerian, you should do yourself. So lecture starts 8 a.m. psychology, 9:50 a.m. chemistry, and then 12 for some groups chemistry subject. So you should be in time. No one's late, and doesn't matter what country you live. To be late, it's a disrespect to teacher. I hope you understand that it's unacceptable. Okay, do you have any questions to ask? Nothing? No translation or no questions? I hope you heard everything. Okay, if there are no questions, the lecture is over. For now, next time we will talk about coordinational compounds or colloidal solution. I will decide then which one first. And be ready, this topic as well as the previous, it's a second submodule information. pH is essential. There are a lot of objectives to explain, some shifting, hydrolysis, and so on. Okay, no questions. Thank you. Goodbye. See you next week. Don't be late next time.